Hello, George Romanic here. Today's video is very interesting. You see the question now on your screen. It's again related to Coriolis force, and it says in part A, using words and simple concepts, demonstrate that Coriolis force does no work, and in part B, demonstrate that same thing using equations. I will talk about part A now, and part B will be the next video. So, how do we talk about Coriolis effect and the fact it doesn't do any work? Well, we really have to go to the beginning and see what is this Coriolis effect and Coriolis force all about. Earth is a non-inertial reference frame. And that's because Earth is rotating, of course, around its axis as well as around Sun and so on, but we are interested about rotation around the axis of Earth's rotation. So that means if you are measuring something in respect to the surface of the Earth is accelerating because rotational motion requires acceleration, and that is non-inertial reference frame. By definition, non-inertial reference frames are those frames that are accelerating. Inertial reference frames are those that are not accelerating, so they are either static or they move at constant velocity. Because according to Einstein, you know that standing still and moving at constant velocity is the same. You cannot make the difference. But you can make the difference if you are accelerating. In straight line or curved line, doesn't matter. So, second Newton's law, F equals ma, in that form, only applies to inertial reference frames. When we go to non-inertial reference frames, such as the rotating Earth, the second Newton's law needs to include apparent forces that arise due to measuring velocity in respect to non-inertial reference frame. And these three forces that arise due to rotation of the Earth are Coriolis force, centrifugal force, and Euler force. Euler force was proportional to the angular acceleration, change of angular velocity with time, and for the time scales that we are interested in everyday life, angular velocity of the Earth is pretty constant, so we neglect that force. So we are left with Coriolis force and centrifugal force. Centrifugal force combines with gravitational force to give us effective gravity. All this is demonstrated in my separate videos. So we are left with Coriolis force. Now, let's take example of the northern hemisphere. Coriolis force deviates motion to the right. Always and exclusively to the right. Now, that means if you have an object that is moving, the force is acting perpendicular to that motion and to the right in northern hemisphere and to the left in the southern hemisphere. I demonstrated that in previous problems numerous times. So if the force is acting perpendicular to the direction of motion, that means there will be no acceleration or deceleration in the direction of motion. So the object will not start moving faster or slower due to Coriolis force. Only direction will be affected. So, to summarize this sentence, what I mean is if we take that the velocity of the object is speed and direction, only direction is affected by Coriolis force. Speed is not affected. And that means, really, Coriolis force does no work. If you have a bullet that is fired and the bullet causes a damage to the target, you cannot claim that the damage is higher because Earth is rotating. You can only claim that the target would be different, namely bullet would hit different point on a non-rotating Earth, but the impact of the bullet would be the same whether or not the Earth is rotating. That is not the case for some other forces. Let's take drag force. The bullet is traveling through the air. Now, depending on the shape of the bullet, drag force will be larger or smaller. If the bullet is very aerodynamic, drag force exerted by the air is smaller than if the bullet has some bluff body dynamics. So you could claim that the damage to the target is different depending on the shape of the bullet, i.e. depending on the drag force, but not in the case of the Coriolis force. Hence, in this case, drag force does work, but Coriolis force doesn't do work. The same, of course, applies to the southern hemisphere. Just direction of deviation is to the left of the direction of the motion, but it's always perpendicular, and any force that is acting perpendicular to the direction of motion does no work, in other words. So that's how you can explain it using simple words. In part B, we will repeat this, but using equations.